Assalamu alaikum. Let us begin our lesson 3 of physical optics. Today we will be discussing the wave theory of light put forward by Christian Huygens. In the last class we started discussing what is a wave and what is a wavefront. What is a wave? It is the periodic disturbance that displaces energy from one place to another in a material medium, but do not displace the particle of the medium. For example, here you can see a water wave. If there is a small disturbance produced here, what happens? A wave is formed or the disturbance is carried along the surface of the water. Now, if you have a small piece of paper on here, what will happen to the piece of paper? Will it move outwards like the wave or will it move up and down?
Up and down.
It will remain in the same position.
It will stay in its own position and it will just move up and down. It will not move outwards with this disturbance. So the wave or the disturbance moves outwards, but the particles will not get displaced. The particles will not get displaced outwards. It will just vibrate up and down. So this is called a wave. Only the disturbance gets displaced or the energy gets displaced, but the particles will not get displaced. Now here we are going to learn a new term called wavefront. What is meant by wavefront? The locus of the particles of the same phase on a wave is called the wavefront. Here, look at this water wave again. Here, if I take a particle, it's moving up. So along this circle, if I consider all the particles, they are all moving up. Now, if I immediately take a nearby point, the particles on that point is moving down. So if I take a circle, along this circle, all the particles are moving down. So we can call all this particle along the circle as having the same phase. So the locus of all particles mean the path of all particles of the same phase on a wave is called a wavefront. Therefore, in this case of water waves on the surface of water, the wavefronts have circular shapes. So what we can see is the circular shape, and this disturbance will move towards outside, but the particles will not move. So this is the case of a water wave on the surface of water. Now here you can see a lighted candle. Here what kind of wave is produced by this lighted candle?
Transverse.
I didn't hear you.
Transverse.
Yeah, it's transverse wave. What wave? This is water wave. This is light waves. Light waves are produced, right? But the candle produces light waves which are transverse. So these light waves, you know, it moves in all directions, 3 dimensions. It is moving, it will be moving forward, backward, sideways. Since this is a 2-dimensional screen, I can show only the 2 dimension. Actually, it is moving in all directions. Now, when we consider a sphere around this candle, along that sphere, all the particles will be in phase. So, the wavefront produced by this candle are spherical in nature. So, for a point source of light, the wavefronts are spherical. Here, you can see the wavefront. Since this is a plane, we can show only 2-dimensionally in the form of circles, but actually it is spherical because it is 3-dimensional. Light wave will be going in all the directions. Now here, in which direction is the wave propagating? It is propagating radially outwards, right? And the wavefronts are circular, which means the wave propagation is always perpendicular to the wavefront. Or you can also consider the wavefront will be perpendicular to the direction of propagation of the wave. Here the light rays travels radially outside along the sphere, and the wavefronts are spherical, which means the wavefronts and the direction of the light ray will be perpendicular to each other. Here there is a figure that shows different types of the source of light, how the light ray goes, and what will be the shape of the wavefront. If it is a point source like a candle, the light rays will be going radially outwards, and the wavefront will be spherical like a ball shape. Here, even if it is shown in a plane, you have to assume that it is spherical, like a sphere. Now here you have a light ray that is coming from a far distance. So if you consider from a far distance, then it appears that all the light rays are parallel to each other. So here the light rays are parallel to each other. So we have to consider the wavefront perpendicular to it. So the wavefront is a plane which is perpendicular to all these parallel light rays. Is this clear to you? You can stop me at any point and ask doubts if it is not clear. Now here you have a straight line source of light, like a tube light. And here light will be going radially from every point, right? So if you consider the wavefront, it will be cylindrical in shape along the cylinder, because if you consider the radially moving light rays in all directions, then it can be cylindrical. Now here,
Teacher,
yes.
can you say what is wavefront? I'm just confused. Like locus, what's the confusing?
Wavefront means the locus or the path of all particles of the same phase. Here in the light rays case, you cannot visualize that idea. That is why I use this case of water waves to show. They are the path of all particles which are in same phase. That here if you take along the circle, you can see that all the particles along the circle at a time will be moving up. So you can call they are all in phase. So the shape of the wavefront is circular. Similarly, if we take all the particles along this circle, they all are moving down. So again, the locus of all the particles which are moving down, which means that all the particles which are in phase is down. So it's in a form of a circle. So for a point source of disturbance, the wavefronts are circular. In the case of light, we cannot visualize the particle moving, but we remember that light is an electromagnetic wave, right? And the electric field and magnetic field go up together, come down together. So if it is going in all the direction, if we take a sphere surrounding the source of light, at that point, all the particles will be in phase. Either they will be moving up or down. Is that clear?
So teacher, every circle is a wavefront.
Yeah, every circle is a wavefront. Suppose light is traveling with a velocity, right? Suppose the light is traveling with a velocity v. We are considering after 1 second. So after 1 second, the light travels with a speed, a distance of v into t, velocity into time. So if you take at that time a circle drawn there with that radius will give you the wavefront at that time. So every circle, it is not compulsory that you have to draw a circle here. Even if you draw a circle here, it will be a wavefront. Even if you draw a circle here, it will be a wavefront. Even if you draw a circle here, it will be a wavefront. Doesn't matter. Just to show, they have shown some circles. Is that clear to you? It need not be exactly at this position. Every circle taken around it or every sphere taken around that point source will be representing a wavefront. Is that clear, Zaman?
Yes, teacher, it's clear.
Okay.
Thank you, teacher.
So when we consider a tube light, it is a line source of light. So light will be emitted radially from throughout its length. So if we want to consider the shape of the wavefront, it will be cylindrical. So light rays will be going radially throughout this length. Now, another case, suppose plain light rays are coming or parallel light rays are coming from a distant source. And if we keep a convex lens here, we know that all the light rays will converge at a point, right? So these are the light rays which are converging at a point. Then, if the light rays are converging at a point, if we consider perpendicular to it, we get spherical shape. So, for converging light rays, the shape of the wavefront will be spherical. Similarly, if parallel light rays are coming and if we keep a concave lens here, what happens? The light rays diverge, right? So these three lines shows diverging light rays. Then also if we consider something which is perpendicular to these, they will be spherical. So we can say that for points...
Perpendicular to what?
Hello? I didn't get you, Khadija.
Perpendicular to what?
Perpendicular to the light rays or
The
perpendicular to the direction in
Teacher?
which the light moves. Yes.
Teacher, can you show like practically how they are perpendicular, like if it's y
I
direction
cannot
and that's
show practically wavefront because wavefront is a imaginary concept.
like if we consider the locus is on the x-axis,
Locus
then
cannot be on the x-axis. Means
like if we take the surface of the water,
Hmm.
it's on x-axis. So the locus is on in the wavefront
Surface
is on
means a plane, right?
yeah, the
Surface
plane.
is a plane. So you cannot take it as an axis. If you consider this as the x-axis, suppose x-axis is lying here and the particles are moving up and down, which means along the y-axis. Okay, so these plane wavefronts will lie in this plane, which means it will go up and down. So you cannot consider that it is in a axis. It will be lying in a plane, but the plane will be perpendicular to the x-axis. Direction of propagation, you can tell it will be along an axis. So if you are considering the wavefront, it will be perpendicular to that axis. That's all you can tell. Here, if you consider this direction of the light rays are along the x-axis, this plane, which is perpendicular to the x-axis, will be the wavefront. Which means if the direction of propagation is x-axis, the wavefront will be in the YZ plane. Now, can you visualize? Practically, I cannot show wavefront because wavefront is an abstract concept. It's an imaginary concept.
So
Zaman? Wavefront is an imaginary concept. It is not physically existing thing which we can visualize, which we can only mentally visualize that. So I try.
Perpendicular to direction of propagation, right?
Yeah, that's it. It's always perpendicular to the direction of propagation. So what I do here is just to give you the concept of wavefront. Okay, so let me go to the Christian Huygens wave theory, then maybe it will become more clear to you. Can I proceed?
Yes.
Teacher.
Okay. So let me proceed. Let us see the Christian Huygens wave theory. So Huygens principle or wave theory, which he put forward in 1678, that is 1678, it tells that all points on a wavefront are the sources of secondary disturbance. See, here, this is a wavefront. Suppose this is a source of light. This dot is a source of light. Then this circle represents a wavefront. Now, all the points on the wavefront are sources of secondary disturbances. So, in Christian Huygens principle, he assumed, this is a theoretical principle, he assumed that all the points on the wavefront will act as a source of light, which means all this can be assumed or imagined as a source of light. So if A is a source of light, it will again give out radiation, or the wavefronts, circular or spherical wavefronts will appear around it. Similarly, if B is a source of light, B will be emitting again spherical wavefront. C will be emitting spherical wavelengths. Like that, D and E will emit spherical wavefront. Now, all these waves are traveling with the same velocity, right? So, after a small time t, they all must have traveled equal distance. So, if you make a sphere with the same radius from all this point, you will get small circles like this. And the envelope of all these circles will give you the next wavefront. Again, if you are considering another time, then again you have to consider these points as source of light, again draw circles, and the envelope of all those circles will give you the next wavefront. Like that. That is how the wave is propagating. So this concept of wavefront is used only by Christian Huygens in his wave theory. It's an abstract theory. So Christian Huygens put forward the wave theory in 1678. And according to him, light travels through a hypothetical medium called ether. See, now we know that light and electromagnetic waves do not require a medium to propagate. But back in 1500s and 1600s, the scientists at that time could not imagine a situation where something can travel without a medium. They could not imagine such a situation. Then they thought that the whole universe is filled up with a hypothetical medium called ether. Okay, so they thought that light, the sun's rays come from sun to earth, and it is through a hypothetical medium which prevails throughout the universe. So Christian Huygens said light travels through a hypothetical medium called ether in the form of a wave from one place to another, and when it reaches our eye, the sensation of vision is produced. Remember, back at that time, people believed that light consists of particles called corpuscles. So this was a revolutionary idea put forward by Christian Huygens. So this medium ether does not exist. It was proved later. In next chapter, you will see Michelson-Morley experiment where they prove that this hypothetical ether doesn't exist. But back in 1600s and 1500s, people believed, the scientists believed that the whole universe is filled up with a medium called ether. So this was what Christian Huygens said. And the principle is that if you are asked to state Huygens wave theory, this is what you have to write, that all points on a wavefront are sources of secondary disturbance, and these secondary waves travel through space with the same velocity as the original wave. And the envelope of all the secondary wavelets after a given interval of time give rise to a secondary wavefront. Zaman asked me, can we draw the sphere at any point? Yes, because if this time is t, if you are taking a smaller time t1, then the sphere will be here. If you are taking a larger time t2, then the sphere will be here. So anywhere you can draw a sphere, the only condition is that the center of the sphere should be the point source of light. Is this clear to you? Christian Huygens wave theory, is it clear to you?
Yes, teacher.
Okay, so now what we are going to do is Christian Huygens wave theory we will use, and we will derive the law of reflection and refraction. As I told you before, Christian Huygens put forward this theory in 1600s, and the scientific world at that time was not ready to accept the Huygens principle. Later, only he theoretically showed that with his principle, he can derive the law of reflection and law of refraction. And also another scientists like Thomas Young and Fresnel showed that light, like other waves, shows the interference phenomena and diffraction phenomena. The scientific world accepted his theory. So now what we are going to see is how Huygens principle can be used to obtain the theory or laws of reflection of light. What is meant by reflection of light? What is meant by reflection of light?
The light will come back.
Yeah, when light is incident on some smooth surfaces, it gets reflected back to the same medium. This is called reflection of light. And do you remember the law of reflection? What is the law of reflection? What is the law of reflection?
Angle of incidence equal to angle of refraction.
Yes, angle of incidence is equal to angle of reflection. I will just explain this figure to you. Then I can show you on whiteboard how this figure is constructed and how using this figure we can derive the law of reflection. So here in this figure, Mn is a reflecting surface or a mirror. This ray is the incident ray, and this ray is another incident ray. So two incident rays of light are shown here. This incident ray meets the surface at the point A, and this incident ray meets the surface at point C. Now these are two parallel light rays coming and incident on this mirror, and the angle of incidence is I. This is the normal. The dotted line is the normal. Angle of incidence is I. Now, after reflection, it will go along this line. This is the reflected ray. So this angle will be the angle of reflection R. Similarly, this light ray will come here and will be incident at the point C. And if we draw a normal here, it gets reflected with the angle R. Now, we know that if you know two light rays, if you draw one line perpendicular to that, that will show you the wavefront. So these two lines are the incident rays. So this line AB is a line drawn perpendicular to both this incident rays. So this represents the incident wavefront.